In this video, we're going to look at zinc-carbon batteries and alkaline batteries. So we're using the word battery here in everyday language. We're really speaking these are not batteries; they are cells. Batteries when you have two or more electrochemical cells connected in series, and you'll see inside these things, both zinc-carbon and alkaline batteries, there's only one cell there. Right, now these are the alkaline batteries are the ones which are used by far and most far and away the most today. Zinc-carbon batteries here they seem to have largely gone out of fashion. You can still buy them, but and people tend not to use them too much because they don't you can't use them for giving a large current for a long period of time, and they're okay for small currents, and they don't last for very long. They last about they can provide about a third as much energy as an alkaline battery. And if you look at them, they're really cheap. If you go on Amazon, you can buy these for about 20p each for a AA, whereas the cheapest price you can get for an alkaline battery is about £1 for an AA battery. Okay. But first of all, we'll have a look at zinc-carbon batteries. And by the way, you don't need to know, you don't have to be able to recall how either of these batteries works for the AQA syllabus. This is just for illustration to show you how we can show how they work given the electrochemical information, and we can discuss some aspects of them just to help further understanding of the topic, but you don't need to be able to recall this yourself. Okay, so here is our zinc-carbon battery. We have got here the positive connection is up there, the positive end of the cell, and that is a carbon rod, which is graphite conductive, down the center of the battery. Now that is surrounded by a layer of manganese dioxide paste, which actually doesn't get involved in electrochemical reactions, as we'll see. Manganese dioxide is a powder, and that's suspended in a paste. And then outside of that, we have an ammonium chloride dissolved in an aqueous paste. It's in a paste rather than in a solution, a jelly, so it doesn't spill. Electrochemical reactions do occur with the ammonium chloride. And then on the outside, this blue layer here is the zinc cover. It's a zinc cover, and that you get electrochemical reactions there. The zinc actually reacts. And as the battery gets old, because the zinc is constantly reacting, that casing will get thinner, and these two, after you leave them, forget about them inside an appliance for a couple of years, you come back and they'll be leaking because the zinc will have reacted away. Right. Let's look at the chemical reactions occurring here. So we have got these two half cell electrode potential values here. Now this is the most negative one, and so that will be best at pushing away electrons. So this one is going to go in the backward direction. This is the most positive, so this is best at pulling in electrons. So that's going to go in the forward direction. You can see there that the in this reaction, the chloride, sorry, there should be two chloride ions there as well. Sorry about that. The chlorine and the nitrogen don't get oxidized or reduced. What's undergoing the redox change there is one of those hydrogens, which will be a +1 oxidation state there. And of course, when it has hydrogen gas, it's a 0 oxidation state there. So we combine those two half equations to write the full equation, which will happen as the cell is discharged. Okay, so we're going to get zinc plus 2 ammonium chlorides is going to give us zinc ions, 2 ammonias, 2 chloride ions, so we get zinc chloride essentially, and hydrogen gas. Now, the hydrogen gas, well, that causes a few problems, because what will happen is the hydrogen will form little tiny bubbles on the surface of the positive contact there, and that can cause an insulating layer, which will cause the battery to stop working. So to get over that, that's where the manganese dioxide paste comes in here. The manganese dioxide will actually oxidize two of those, it will oxidize hydrogen to water, and you get manganese 3 oxide, Mn2O3, and you'll get H2O. So that's what the manganese dioxide paste is required for. And as I say, these batteries are very old-fashioned. No one really uses them anymore, but when I was a kid, and for torches and radios and stuff like that, you'd use these, and if you use them a lot, they tend to stop working. They go dead, but they hadn't really run out. And the reason why they go dead is because you get an accumulation of hydrogen on the carbon rod there. So if you got those, took them out and put them in a hot place on a radiator or something, well, first of all, that hydrogen would diffuse away more rapidly, and also it would react more rapidly with the manganese dioxide, so it would clear it. So after 20 minutes or so in a warm place, the batteries sort of come back to life for a bit. As I say, they're not really very good. They're not good at delivering good current, strong, large current for a period of time, because of the hydrogen will build up, and they can't store as much energy as an alkaline battery. Another thing is with the hydrogen here, if you look, well, we know if you want to recharge a battery, you have to make, you connect it up to a volt, to potential difference, and push the electrons away they don't want to go. You make the cell go backwards. Well, you can't do that with this battery, because you make hydrogen, you need hydrogen to go voltage backwards, and of course the hydrogen will diffuse away or react to form water, so you don't have that anymore. So it's impossible to recharge those batteries. Right, let's have a look at alkaline batteries, which is the case, of course, I said, are the ones which are much more commonly used nowadays. Right, let's have a look at the structure of it here on the left. Right, so the negative electrode in this case is it's actually zinc in powder form. Okay, that's going to react. The reason why it's in powder form is to increase its surface area, and then there's actually a zinc rod there to collect the current, and that forms the negative pole of the cell. Right, the green layer here, well, that is just a salt bridge to separate the two half reactions, and the blue is manganese dioxide, and that is that's in an alkaline paste of potassium hydroxide. We'll see why it needs to be alkaline in a minute. And that is connected to this metal casing here, which forms the positive connection, and then we have like this red on the outside. That's just insulation. Right, so let's look at what happens with this reaction. So look at the electrode potential values. This is negative. Okay, so this is going to be going backwards. This one is going to go pushing away electrons. That's going to go that way. This is the most positive one, so this is going to be taking in the electrons and going forwards there. So we write an overall reaction for that, and we are going to have zinc and 2OH minus is going to react with 2 manganese 4 oxides, manganese dioxides, and water, and that is going to give us zinc oxide and water and Mn2O3 and 2OH minus. Okay, so we can see that we can cancel out those OH minuses on both sides of the equation. They don't actually take part in the reaction, and the water also cancels out. There's that. So that's the overall reaction. We've got zinc, manganese dioxide going to zinc oxide, and manganese 3 oxide. So could we recharge this? Can you make this go backwards? Well, theoretically, you could make it go backwards, because there is no the hydrogen, like in the other case, the hydrogen escapes. That doesn't happen here. And can you recharge alkaline cells? Well, it says not to, always on the packet, because if you do, they tend to get too hot and then they split and then they stop working altogether. Also, they get too hot, they can catch fire or something. But you can recharge them, and you can recharge them like once or twice. They don't really work. They're never ever as good as they were in the first place when they were new, but you can actually recharge them a little bit. I say alkaline cells are they deliver a lot more current, but about 3 times as much energy stored in an alkaline cell compared to a zinc-carbon cell. But if we actually look at the two reactions, we can actually see they're both very similar. So we just do the zinc-carbon there to remind ourselves. What happens there is zinc is oxidized to Zn2+. What happens in the alkaline cell is, of course, we get zinc going to the zinc 2+ oxidation state in zinc oxide. So that's really the same, and that's essentially where the energy is coming from in both of these cells. Oxidation of zinc is an exothermic reaction, and that's where the energy is coming from. The difference is in the oxidizing agent. In the zinc-carbon, well, the initial oxidizing agent is ammonium chloride, and of course that ends up making hydrogen. Whereas the oxidizing agent in the alkaline cell is MnO2, which ends up making, it's reduced to that. But of course we saw that, well, this hydrogen, you get rid of the hydrogen by you oxidize that with manganese dioxide. So not really, the overall reaction really in each of the cells is very similar. They just carried out in the different conditions. But really the energy is coming from the oxidation of the zinc to Zn2+ there. Right, you don't need to know the details of that, but there's just a few useful, interesting things going on there which help you understand this topic a little bit better. And if you look at past paper questions, very often they'll give you, they've never used these two examples, but they'll give you a practical cell which is used to deliver current, and you have to make these kind of judgments and understand it yourself.